I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired operating systems engineer from Microsoft, going back to the MS-DOS and Windows 95 days. And today, we're going to try to build something really cool. It's something I've wanted to make for almost 35 years, ever since I saw my first example of one back in high school. And I don't mean a cheerleader robot. So first, let me show you where we are going today. We're going to build a 16-band music spectrum analyzer, and it's all done on a Commodore 64 in full assembly language at up to 40 frames per second. Here are a couple of demos that show it in action. First, we have Shout, which opens with some high notes that show the frequency bars lighting up selectively up at the top of the range. Now take a look at Owner of a Lonely Heart with some distorted guitar that leaves a couple of bands completely open to the drums coming in. Next, we have Walk of Life that begins with organ notes down in the mid to low range before the rest of the song hits. And finally, a few seconds from Addicted to Love. Pay attention to the VU meter and how the bass beats alternate with the other drums to confirm a lack of any real latency. Okay, more demos later, but you get the idea. So how do you actually build one, and why have I wanted to make one ever since high school? A mic-equipped ESP32 captures the audio as CD quality and then splits it via FFT into 16 frequency bands. Those bins are then sent at high speed to the C64's user port via some fast proprietary serial bit banging, and the 64 renders the audio visualizations. Well, back then, we had an actual super genius in our computer science club named John, and John was also pretty good with hardware. He had taken his Commodore PET and he'd built a board for it that had a bunch of high, low, and bandpass filters on it. He had then even built his own successive approximation DAC, or digital to analog converter, in order to digitize the audio input. This all lived on a daughter PCB inside of his Commodore PET, and it connected with the computer's user ports to transmit the band data from his board over to the assembly language code that he'd written on the PET side. The PET would receive the numbers for each band and then draw what a lot of people mistakenly call an equalizer, but is really a spectrum analyzer. It looked cool and smooth and way above the PET's pay grade to be displaying anything like a live audio spectrum quite like that. I've long wanted to replicate his project, but I lacked the hardware skills to do it. Until a year or two ago, I didn't even know where to begin really, but I've been practicing. And the thing is, I've already written a spectrum analyzer for the ESP32 chip. There's a complete code review of it already right here on the channel. Thus, all I would have to do is interface that one with the PET somehow and then have it draw the visuals. I decided that I'd use an MCU to replace all the filters and gates and 74 LS series chips that John likely used in the original. An ESP32 has the math chops to crank out a decent FFT 40 times a second, all while sampling the audio at CD quality rates, so it does all the audio heavy lifting for us. You could use any ESP32, but since the little orange M5 stick here has a built-in microphone and even a color OLED screen for monitoring the spectrum, it's a natural target for it. But even if the spectrum side is already done, how am I going to get the data from the ESP32 into the PET? I'd been discussing the project with my friend Rutger, who manages all of my channel's source code assets from the Netherlands. I was trying to convince him to join in and code on this project, and that's when I realized that I had to make it a C64 project. The simple reason is that the PET and the C64 are very different from one another on the I/O side. The PET doesn't even have a serial port, let alone a well-defined kernel interface for talking to it. But the 64 has both. If you can forego flow control and other niceties like ring detection, you really only need the ground and then two wires, transmit and receive. But with only two lines, how would you know when to receive and when to send? Well, with RS-232, everything about the protocol is timing-based. There's no clock or control lines to contend with. At 2400 baud, you receive a bit, and then 1/2400th of a second later, you do it again. All I needed then was a pair of I/O lines on the ESP32 that I could use as a serial port. The ESP32 chip actually has 3 UARTs, or serial ports. I needed to keep one for programming and monitoring, but that left at least one free for my own use. The only problem was which GPIO pins it would be attached to. There's a small 4-pin connector on the end of the M5, and it exposes two general-purpose I/O lines, pins 32 and 33. I figured the odds that those lines happen to be the real RX and TX were low, so I used the Software Serial class, which allows you to create the new serial port on any two arbitrary pins completely in software. Later, I would learn that the I/O pins for the UARTs and the ESP32 are actually assignable, meaning I was able to later switch it over to the normal hardware RS-232 and make use of it that way, which uses a lot less CPU than the software version. The first thing I needed to do then was to wire up a cable to go between the ESP32 and the 64's user port. Normally it might only be an inch or two long, but my dev machine is on the other end of my bench, so it was more like 12 feet of wire. I connected RX and TX to the two GPIO pins and ground to ground. Unfortunately, the 5-volt line on the M5's 4-pin connector is output only, so the M5 needs to be powered by USB, its internal battery, or you can run that 5 volts around to the other end of the M5 and plug it into the power input over there. Now the thing about the 64 side is that it really isn't classic RS-232, because real RS-232 uses 12-volt signaling, which gives it better range over long cables and better noise resistance. But instead of 12 volts, the 64 puts out 5-volt signals. Normally, we need to convert them up to 12 volts and also invert them, but guess what? The ESP32 I'm using operates at 3.3 volts, so 5 is actually a lot better than 12 in our case. While I technically should be using level converters to bring mine up from 3.3 to 5, it turns out they're not strictly necessary for proper results, so in order to keep it simple, I'm just not using any in the initial development. Your mileage may vary, but I've not had a problem yet. In order to see if I was able to exchange any data, I needed a simple terminal program on the 64 side. I planned to merely printf some content from the ESP32 to see if I could get the 64 to display it. So I wrote up a little basic app to do exactly that. Open the modem port with the classic old open 2,2,2, and then read from it and print anything that it received. And then scan the keyboard, printing any input, and sending it on through the serial port back to the ESP32. Within a few minutes, success. Up came the initial boot screen of the Whopper computer from War Games, which is the actual text I was sending over from the ESP32. Confident that I would now be able to send the peak data over from the ESP32 in similar fashion, it was time to turn my attention to drawing. I was going to draw a spectrum analyzer with 16 bars, so drawing one bar would need to be my first task. And drawing a bar starts with drawing a rectangle. So to that end, I wrote an assembly language function that would draw a rectangle on the screen using Pesky characters. First, it would plug in the top left and top right corner pieces. Next, it would draw a horizontal line between them. Then it would draw the two vertical sides of the shape before finally poking in the bottom corners and then drawing the horizontal bottom line between them. It may not be the fastest way to draw a tall bar, but it was flexible and it looked nice. I wrote up a little test app to draw a series of nested squares. My initial implementation even allowed for overlapping sections where a horizontal line would cross with a vertical and it would turn into a plus sign, for example, but the reality is that we just won't have that happening, and so I ultimately removed that logic in favor of faster drawing. With the box draw code working, it was time to draw 16 tall skinny rectangles and call them bars, so that's precisely what I did next. My following step after that was to make them animate by scrolling the values in the little table that I was using to hold their heights. This would have the visual effect of scrolling the bar heights themselves, thereby animating all the bars every frame and giving me a sense of what performance will be like once I have sound and data running. Now, premature optimization is the root of a lot of evil. Not all evil, but a lot of it. I believe in making it work first and then making it fast later. I don't mean you should write some ham-fisted approach that you throw away, but don't worry about every cycle up front. As long as it's in the ballpark of fast enough, it'll do. I would improve the speed of this a lot later, but it was already pretty good being in assembly. At this point, I was still planning to target both the PET and the 64, so I had the code running on both through a set of include files that Rutger and I had concocted to allow for the differences between the two machines. And now that I had some semblance of bars rendering, I needed to look at getting the real data from the ESP32 to the C64 for rendering. The problem was that I had never written any assembly language I/O code for the PET and 64, and when I looked into it, I realized it was going to be very difficult to write code for both in a cross-platform fashion. For one, they use different I/O chips. The PET uses the older 6522 Versatile Interface Adapter, or VIA, whereas the C64 uses the 6526 CIA, or Complex Interface Adapter. Moreover, the 64 organizes its code into a set of reasonably standardized kernel routines that allow you to do things like open a device, get an output stream, and send data to it. Early versions of that code may very well exist somewhere in the PET ROMs, but it's all undocumented and undoubtedly very different than the 64 version. So it was at that point that Rutger and I agreed to make this project 64 only for now, so that we could focus on making the serial code really optimal. Although we wouldn't do anything to intentionally complicate a future PET version, for now I would leave that work to others. So if you know something about exchanging data with a PET through the user port, please join the GitHub in the video description, dive on in, and make it work. Until then, it targets the 64 only for now. This was the last time that the code ran on the PET, and so at that time I also supported both 40 and 80 columns. The next step in the quest was to be able to receive data from the ESP32, which would allow me to connect the VU meter and the bars to live audio data. For now, though, I would have to be content with fake data. And so, on the PC side, on the serial monitor, I recorded a bunch of output from the spectrum analyzer in a manner that allowed me to encode that data into a byte table for the assembler to process. I'd then bake that data into the project, and the analyzer would be able to run in demo mode with this fake data at any time, which would make development and debugging significantly easier in these early stages, particularly for Rutger, who doesn't actually have a Commodore 64. Did you know that there are still children in the world without access to a Commodore 64? Poor little Rutger. He worked so hard creating software for free for the masses, but he has access only to the Vice emulator. I'd love to surprise him with a decent 64 or 128 so that he can actually see the projects he's working on, but it's a long way to ship things to the Netherlands. So if any fellow coding Dutchmen have a spare 64 and maybe even a monitor they consider boxing up and sending to him, I would happily cover any domestic shipping and stuff like that. Let me know in the comments. To enable demo mode, I added code to simply copy frames from the fake data table into the peak data band info once per frame, and then advance and wrap around the fake data table so that it plays in a loop. It works great, and this way I can test walking before I try to code running. And as I get ready to run, though, the next hurdle I'll have to jump is to get the serial data from the ESP32 into the 64 in assembly language, something I've never done before. The most the 64 can pull off is 2400 baud, and that's with some fixes. But assuming I can get there, that's 2400 bits per second. There are 16 bands, so if I allocate a byte each and one additional byte for the overall VU, that's 17 data bytes per frame packet. Add a magic ID up front and a null terminator on the end, and you're at 19, so let's round up and call it 20 bytes. That's only going to be 12 frames per second. That just won't do. It just won't be smooth enough. But if I pack 2 bars into a byte by giving each bar 4 bits, it almost doubles my data rate. It does mean that bars are limited to a height of 0 to 15, but given there's a border and a top and bottom margin, that might turn out okay. If I pack 2 bars into each byte, plus a magic byte, VU byte, and null terminator, I'm at 11 bytes or 88 bits. At 2400 per second, that's 27 frames per second. Movies are only 24, so it's likely smooth enough. And if it turns out not to be, we can do the bar decay locally at infinite frames per second and just get the new peaks 24 times a second, and I bet that would look pretty great. So I'm pretty sure 2400 baud is going to be just fast enough. The problem is the 64 serial code has some bugs and some major inefficiencies. Like for every bit, they restart the CIA timers rather than just leaving them running in continuous free running mode. It also eats and translates nulls without your consent, stuff like that. I found a great old article in the Transactor magazine from 1989 that included code for a set of 2400 baud routines. I was just about to leave on vacation, so I asked Rutger to have a look. He found a GitHub project that had also developed and refined the Transactor code a little further yet, and so he used that as a starting point. And sure enough, by the time I got back from vacation, he had checked in serial code that he had inserted and fine-tuned without ever being able to test it. He also had removed some self-modifying code that had been present in order to replace it with a table-driven approach, so the changes were not all that trivial. What were the odds that it could possibly work? Well, I'd find out soon enough. I got underway on my own mission of getting that serial code to run on the real 64 at 2400 baud and receive some data. In short order, I had some garbled text, and then a few minutes later, I had the strings appearing that I was looking for, and I was receiving Hello World that I'd been sending from the ESP32. Success, at least in part. My next test was to encode the instantaneous VU data and send it from the ESP32 to the 64. I sent it as a plain string, VU colon and a number, and I just had the 64 blindly print whatever it received. Soon enough, I was receiving a stream of VU values scrolling up the screen, and better yet, it was connected to the instantaneous volume level in the room, so if I clapped my hands, the number peaked immediately and then faded away as it was designed to do. Now I had to see if I could send a binary packet including the band peak values, receive and process it, and then repeat that in a constant stream to achieve a decent frame rate. So first, I wrote code on the ESP32 to hand code and hand pack the nibbles with an increasing set of values, 0, 1, 2, and so on up through 15. That way I'd immediately recognize it when it was finally displaying the right values. On the 64 side, I wrote the code to unpack the nibbles and put them into the peaks table instead of using the fake data. It all worked, but this was still using the flaky factory serial routines at 1200. It was time to flip the switch over to our shiny new serial driver in 2400 baud. It actually went surprisingly smoothly, given that I was integrating code from someone that I'd never met on the other side of the world who wrote the code without ever being able to run it. But in short order, I had the code receiving at 2400, and here's a little secret. It works at 4800 as well. Let's take a quick look at the get and put serial cares, as if you're like me, it's something you've always wondered about but never actually had to do. How to send and receive high-speed data on the serial port in assembly language on the Commodore 64. Well, maybe it's just me. Let's get started with get serial care. It specifies the device ID, which is 2, as the current input device. It then checks to see if we have any data in the buffer, and if not, returns an error code. But if we do have data, we pull it out of the buffer and return it to the caller. We have to work around an oddity in the system kernel here that normally does not allow nulls to be returned, so we enable that here. Rather than relying on an in-band null to indicate no data, we now use an in-band FF combined with an out-of-band error code, so that both have to be checked before you can actually conclude that no data is available, and that allows for returning any arbitrary 8-bit value. Put serial care is similarly simple. We specify device 2, call chkout to specify the output device, and then call bsout to send the character. We actually have already hooked bsout to insert our own more, faster, better version, so let's have a quick look at that. It's not simple. It stores a value in the buffer, and when that buffer is full, it begins transmitting the serial data. We actually load the timer with the bit times needed for each serial bit, and then we bit bang the port manually. Once the timer is loaded with the on times for the bit, we start the timer and we'll let it rip for each bit. I was having some trouble getting the NMIs to actually start, however. No matter what I tried, serial data wouldn't start until I pressed the restore key for some reason, and then it worked perfectly. It was so odd. And then I got an email from Rutger who found the bug. When he had translated all the hex addresses in the original code over to nice labels, he'd gotten one wrong and the interrupt control register wasn't being properly set. That fixed that, and no more hitting the restore key to get things rolling. But why did that work? Because in the serial code, there's a special case to account for the restore key, which actually generates an NMI, or non-maskable interrupt, of its own and triggers our code just like a serial bit would. But we note that it's the key and not the serial timer, and we give control off to that code path, which also happened to set the control registers properly for us. So it really worked by accident. But with that fixed, packets started arriving and they were malformed. You can't debug the serial transmission in the emulator, or at least I wouldn't be able to until much later, and so I had to debug it on the real 64. The only problem was that Supermon seemed to get trashed by our code. It couldn't even dump memory when invoked by a break instruction that I had inserted to fire when a packet was received. Thankfully, back when I was 15 years old, a good friend named Rob also had a C64, and he had a cool cartridge for it called HESMON, which was a great machine language monitor. As I had always coveted it, when I found a copy on eBay once, I threw it in a drawer and just in case I would need it at some future point in time, and that time had arrived. I popped out the ubiquitous fast load cartridge and popped in HESMON. It took seemingly forever to load my code, even though the program was only 6K, including that fake data. But without fast load, it's brutal. HESMON enabled me to find the bug. When two adjacent nibbles both contained 15, it wound up being FF and hex, which at that time I was still treating as the end of packet. I simply added code to ensure that I only did so when it was at the right position in the frame buffer, and that solved that. Without HESMON, though, it would have been a lot harder to find. With that bug fixed, the Spectrum Analyzer sprung to life.
Here's Only the Good Die Young by Billy Joel on Amazon Music.
To make sure it's accurate, I did a test tone sweep. It's a little annoying to listen to, but it shows how selective the bands actually are, as the peak goes back and forth as a single bar in response to the frequency sweep. I added visual style definitions and Rutger added color schemes, and between the two, you can get some nice looks. It's also easy to skin to your own taste by simply defining a new visual style in the code tables. By all means, if you'd like to contribute to the project, even just adding new styles, simply stop by the GitHub link in the video description. Here's a demo of the code as it sits today, and I'll step through the video styles and color schemes as well so you can see them as we go. The song is called 238, and it's performed by my son's band, SumSun. You can learn about the song in the video description. I'll also add channel markers in case you want to skip ahead at any point. Of course, if you or your mom is a big cheese AR person with Sony Capital or a similar label, this is from an unsigned album debuting in March, so if you like it, you know what to do.
It's 2:30, I know you're half awake. Can we talk it out? Can we talk it out? I am conversing with myself, and I can't get to know why I am back up on the shelf. It feels like a second home. Am I wasting time? Try to paint a picture, but I'm colorblind. try to keep my thoughts at bay, but the water's still so rough. Last time you said we'd be okay, but now it's not enough. I'm not wasting time, try to paint a picture, but I'm colorblind. Can we compromise? I'll be waiting for you. It's 2:30, I know you're half awake. Can we talk it out? Can we talk it out? It's breaking my brain, saying, for goodness sake, can we talk it out? Can we talk it out?
Well, there's a lot more to talk about, like how I then got it all working at 4800 baud and 40 FPS, running in the emulator over Wi-Fi without cables and so on, but that will have to wait for a follow-up episode. This type of technical episode often doesn't do that well on my channel, even though I love to do them. So whether that follow-up episode happens will depend on a few things. The number of new subscribers that this topic generates, the number of views it gets from the current subscribers, and your likes and comments below. If you do want to see more about this project, please like the video and let me know in the comments which aspect you'd like to see more details on. I'm happy to even do a code walkthrough of the interesting pieces if there's sufficient interest, and I could show you how to run and play it under the Vice emulator so you don't even need to bust out a 64 to make it work. If you have any interest in matters related to autism or Asperger's, or just want more stories from my Microsoft years, check out my book on Amazon, Secrets of the Autistic Millionaire. Click the link in the video description to read the sample chapter, Burgers with Bill Gates. I hope you like it. As always, I'm mostly in this for the subs and likes, so please leave me one of each before you go. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.
4 times Zoom.